find an interval minus c to c, which f maps to itself. Okay, so the values of arctan lie between pi over 2 and negative pi over 2. And so f of x lies between pi over 2 plus 1 and negative pi over 2 plus 1. So in absolute value, pi over 2 plus 1 is larger. So if we take c to be pi over 2 plus 1, then f will map the whole real line into the interval negative c to c. In particular, if you restrict it to negative cc, then it will map that interval back to itself.
Does it work with any values larger than pi over 2 plus 1?
Sure.
It does, okay.
20 over 2. So any larger c will work. But the important thing is that there is one value, and then we want to know whether the equation 2x equals f of x has a solution in this interval. So we need to show that we're dealing with a contraction. Well, really, we're trying to solve the equation x is equal to f of x divided by 2. And the derivative of f of x divided by 2 is 1/2 of derivative of arctan is 1 over 1 plus x squared, so 1 over 1 plus x squared. And the biggest this could ever be is when x is at its smallest, which is 0. So this is less than or equal to 1/2. And so by the mean value theorem, f of x over 2 is a contraction. You can take the contraction constant to be 1/2. And therefore, by the contraction mapping, theorem, x equals f of x over 2 has a unique solution in negative cc. Now, the question doesn't ask for this, but if you were asked, does it have a unique solution in R, the answer is yes, because if you had two solutions, you could take C large enough to include both. And then this would contradict the contraction mapping theorem. It says there's a unique solution.
But the contraction mapping theorem applied when f mapped from M to M, but in this case you have capital R to...
No, I'm restricting to the interval minus C to C. Once I know that the function maps the whole real line into minus C to C, I can restrict it to minus CC. So, in fact, f maps minus CC into minus CC. There's no requirement of being onto or anything like that. Its image should be in the original set. So once you have it, if it maps a larger set into the smaller set, then it also maps the smaller set into the smaller set. 169 at 7. I'll just let it run, and you can have, say, till 10 do the test. So time shouldn't be an issue.
I was also wondering, you haven't returned out homework 7?
Could I do?
And you haven't returned out homework 7, like the homework that was due on Monday?
Right. I'll put up solutions for that today, but if you have a specific question, I'm not sure I have the homework with me. Do you recall a problem?
I don't have any question, I just wanted to get it back.
Oh, get it back, no. No. My grader won't have had time to go through it. It takes a long time to go through somewhat. Okay, but I'll make sure the solutions are on the web page. Have a look at those. Any other questions? Anything from the theory that you want me to go over? Okay, in that case, let me do one more theorem, just as an illustration of what these things can do. Oh, and just another reminder, so there'll be no class on Friday, but we'll meet Monday, and I'll return the tests at that time. Okay, so this is about something that I'm sure you've all met, the Laplace transform. So the Laplace transform is defined for functions f of x, and the transform of f evaluated at s is the integral from 0 to infinity f of t e to the negative st t. So this is useful whenever you're dealing with differential equations. Now, in order to have it defined, this requires that the integral exists for s greater or equal to some value s0. There are functions for which that integral, for example, e to the t squared, that integral would always be infinite, no matter what the value of s. But as long as you're dealing with functions, so that when you multiply it by some large negative exponential, you find that it's integrable, then the Laplace transform is defined. And the theorem is if f is continuous, S0t dt exists, for some value of S0, now the Laplace transform is only useful, what you normally do is you transform an equation, figure out what the Laplace transform is, and then invert it to come back. But if you could come back to two different functions, then the Laplace transform would be useless. So, if the Laplace transform of f is always 0, then the function itself is 0. And so what this theorem enables you to do, it says, if you know the Laplace transform of f, then you know f. Basically, it's a one-to-one transformation.
Is it if LFS equals to here, then
Oh.
So the first
Implies.
refers
So if we have a continuous function for which the Laplace transform is defined, if it always turns out to be 0, then the function was 0 originally. Thanks. So the proof I'm stating it only for continuous functions, but it's true more generally. You just need integral functions, but this setting is enough. This is usually where you apply it. And so the proof goes as follows. Since the integral f of t e to the negative S0t dt exists, let us put g of t is equal to f of t e to the negative S0 of t. So if the transform of f is always 0, then we will have that the transform of g is always 0. Because the transform of g is the integral g of t e to the negative st dt, and that is the integral 0 to infinity f of t e to the negative S0 plus st dt, which is 0. So let's just work with g. If we can find that g is 0, then it will follow that f is 0. So we prove that g is the 0 function. g of t0 is not 0, then we may assume that g of t0 is strictly positive, otherwise we'll just replace g by minus g. And there is an interval of the form t0 minus delta, t0 plus delta, on which g of t must be at least its value at t0 divided by 2. So if we look at the picture, here's our function g. It's non-zero at some point t0, and so we can get some interval t0 minus delta, t0 plus delta, so that on that interval we're above t0, f of t0 over 2.
F of t0 or g of t0?
G. Right. So let us choose a function so that h of t is 0 outside t0 minus delta, t0 plus delta, and is 1 on t0 minus delta over 2 to t0 plus delta over 2. Anything will do. So the function h should look like this. You can even take it piecewise linear. This would be h. The point of doing this is that the product g of t, h of t, now h only has a non-zero value where g is positive. So g of t, h of t is always greater or equal to 0, and so the integral g of t, h of t dt from 0 to infinity is certainly at least its integral from t0 minus delta over 2 to t0 plus delta over 2. On that interval, h is 1, so we're integrating g on that interval, and g is always above g of t0 over 2. So this is at least g of t0 over 2 times the interval length, which is delta. So that's a strictly positive quantity. So given epsilon greater than 0, notice that this function h is continuous and beyond a certain point it's identically 0. So you just did a homework problem that deals with this situation. By homework, there is a function k of t, which is a sum of exponentials n equals 0 to capital N, so that the infinity norm of h minus k is less than epsilon. If we let t go to infinity, we're far enough out, h is 0, and for k, all the negative exponentials die off, leaving you only with the constant term. So if we let t go to infinity, we get that the absolute value of alpha 0 is less than epsilon. And consequently, so at the cost of another epsilon, just by subtracting off the constant term, we may assume that k of t is the sum, not starting at 0, but starting at 1, alpha n e to the negative t. And the infinity norm of h minus k of t will then be at most 2 epsilon. Right, so because these are all negative exponentials, when we multiply by g and integrate, since we're assuming the Laplace transform is 0, the integral of g against any negative exponential is going to be 0. We get that since the Laplace transform of g is the 0 function. And therefore, when we integrate g against our function h of t, in absolute value, we can write it as g of t, h of t minus k of t, plus g of t, k of t dt. This last bit is 0, And we can estimate this. This is less than or equal to the integral from 0 to infinity, absolute value g of t times epsilon. To epsilon. That is true for all epsilon. So now let epsilon go to 0. And what you get is that the integral from 0 to infinity, g of t, h of t, is equal to 0. But we specifically chose h so that this was a strictly positive quantity. So this is a contradiction. And so that shows then that the Laplace transform is a one-to-one mapping, and therefore it can be used in solving differential equations. Wherever it's needed, this is going to work. So you take the transform, then you figure out what the transform is, and then you come back. You're guaranteed to get a unique solution that way. This is not the only way of doing this, but it's a nice application of the Stone-Weierstrass theorem in a situation where it doesn't seem that it might apply. Okay, so that definitely concludes the course. There's one thing left today. Since we're not meeting much after this, I need to do the